Okay, so chapter 3, here we go into a person right before we started filming said, are we doing real algebra today? I said, yes, this is real algebra today. So we're solving equations, having a conversation first that we've had before. If you've had me for other maths, your other teachers may have had these conversations with you. But I usually do an analogy with you. If you had me for 7th grade, we certainly did this together. But I made the analogy that an equation is like a something. Anybody memory of that? It's an old school thing, like back in the days of King Arthur and the Round Table, and witches and wizards, and castles and knights. There aren't witches and wizards.
Oh, is it that weighing thing?
Yeah. That weighing thing. What's that called?
Oh, a scale.
It's called a scale. So in like the olden days, not like you getting on your bathroom scale, but in the olden days, how did these scale things work?
It was bigger on like that side.
Whatever's heavier goes up.
Yeah, the heavier, if they're not in balance, the heavier side goes clonk, and the lighter side goes up in the air. So if you wanted to weigh something, if you're in medieval times and that you have some item that's like 14 pounds in reality, but you don't know what it weighs, and you put your 14-pound item on the scale, how would a person try to weigh it? Because if all you did is put your 14 pounds on the scale, it just goes clonk, it sits there forever. What would they do over here?
Put something else on it.
Put something else on it. And it wouldn't just be like random items. They'd have, what would they have on hand? Weights. So they'd eyeball your item and think, all right, maybe that's about 10 pounds. So they'd throw a 14 over here, they'd throw a 10 over there, and it would go clunk. And they'd think, all right, well, it's more than 10. They'd grab their 5-pound weight, throw their 5 over here, the 10's already there, they throw on a 5, and now it would go the other way, clunk. So then they're like, all right, well, that didn't work. Take off the 5, and then let's throw some 1s on there, 11, 12, 13. And when they hit the magic 14 mark, the two sides will go, they'll be perfectly even. And they balance out. So that's my analogy for you is, these equations we're going to solve today, they're like a scale, those old-time scales, but they're in balance. And they're going to stay in balance as long as you do a certain thing as we do math. What would you have to do if you wanted to keep this scale in balance? Yeah, so let's say we added another pound over here.
You'd have to add a pound.
You'd have to add a pound over there. So one of our key algebra ideas is we're always going to do the same thing to both sides. Because if we do the same thing to both sides, we keep these scales, these equations, we keep them balanced, and that's our goal. In terms of algebra and solving the mysteries of life and getting missing numbers figured out, what's another thing that we have to do? Always do the opposite of what the variable is doing. So if you can find yourself your variable and see what's happening to the variable, we're going to do the opposite of what the variable is having done to it. And then later, when you're done, how can you check these equations? Yeah. We want to replace the variable with your solution. And that's something we spent some time doing last chapter. We had a day about replacement sets and solution sets and zeros and ones and negative ones, that lesson. That was basically there to help you practice checking before we even had things to check. But if you have a solution and you think it's right, you plug it in and you check it. But that's like the main point of algebra is doing opposites. And whatever you do to one side, you have to do the same thing to the other side to keep it in balance. There's a thing that this operates on today called the addition property of equality. I'm not going to make you memorize the addition property of equality for quizzes like we did the commutative properties and some of those other ones. But the addition property of equality does about half the problems today. Basically, it tells you if you have equal things and you add the same item on both sides, those two sides still have to be equal. That's the addition property of equality. The other half of your problems work on a thing that I abbreviated SPE. What do you think that is about?
Subtraction.
Subtraction property of equality. The subtraction property of equality just tells you if you have equal things, they would stay equal if you
Subtract them.
subtract the same on.
Both sides.
Okay, so that might look like A
Minus C.
equals,
B minus C.
and that's our ideas. Okay, that's the ideas of the day with some properties to boot. If we are going to be doing a bunch of adding and subtracting today, we probably still need to refresh what those rules are. So, adding rules, 2 positives makes positive, and we
F.
add. 2 negatives makes
Bigger negative.
negative, and we add. When we get one of each,
Depends on bigger subtract.
depends on bigger, and we subtract. Subtracting, there's a lot of ways you could manage subtracting. Subtracting and adding, they're really like the same. They're opposites, they're the same at their heart. But if we want to refresh those, positive minus positive, how's that go?
If the first is bigger, then it's positive.
We get a positive only if the first one's bigger. If the first one's not bigger, then we'd have to go
Negative.
negative. If you have a negative minus a positive, where's that take us?
Bigger negative.
Bigger negatives. And then the last rule that does about half the subtracting problems in the universe,
Negative minus negative.
2 minuses in a row,
Oh, minus minus makes plus.
makes it into a plus, and then you're like, switch gears into the adding world. Those are the ideas behind today. It's the ideas behind the chapter. It's the idea behind the whole like construction of algebra. We have this balanced out, scale, equal thing. We need to do the same thing to both sides to keep it balanced. And to unravel the mysteries of what the variable means, we have to do the opposite of what the variable is doing. And checking is always a great value in math or life or pretty much anything. Question about the ideas? So here's this done for you a different way, I guess. I mean, you can look at this equation also like a story. So once upon a time, I had a number, and then I subtracted 5. And by the end of my story, that number was 7, and they lived happily ever after. So if you want to figure out what the variable is and like reverse that story, we're back to the ideas from a second ago. You want to always just do the opposite. So if you see this subtracting 5, if once upon a time I had a number and then it subtracted 5 and they lived happily ever after with 7, for you to figure out what that number was before I subtracted, you just have to add to work your way back in time. And the answer off of this is 12. Tomorrow, if you give me a paper and you just write number 1 is 12, I'm going to not give you credit for your homework, and then you may get grouchy with me. The main point of this homework today, like it is every year, is not as much that you get to 12. I'd like you to get to 12. It's important to get to 12. But the thing that we want to really pound into your brain over the course of the year together is the main ideas, which is we always want to do the opposite, and whatever we do on one side, we do to the other. So to pound that in there, just like I used to in 7th grade, I'm going to make you show some work. So here's what I'm hunting is, if you see subtracting, you've got to show me adding. So you're going to add over here, you're going to add over there. If we're going to add to one side, we have to add to the other. The magic number we're adding with is 5. Not 7, but 5. 5's the magic number because 5 is with the variable. The variable is the key to the operation. We add this up. What happens in the same area if you subtract 5 and add 5, like at the same time? It just zeroes out. So I have you cross that out. And in the end, the magic number of what x equals is 12. The 12 that we alluded to when I told you the once upon a time story. If you do all of that, I'm still going to slightly criticize you, because what's one more main idea that we talked about over the idea section? Check it. You want to check it. Is 12 minus 5 indeed 7? Yes. So to show me you checked it, a little check. Question about what I'm making you do. Yeah.
Do you want us to show our check mark? Or can-
Yeah, put a little check mark. Then I know you checked it, or I know that you're fibbing. If you have a wrong answer with a check mark beside it, then I know you're a big fibber. On the board, in class, it always seems like checking is pointless. Why do you get the false impression in class on the board that checking is pointless, when in reality, on your homework and on your quizzes and on your tests, checking is very helpful. But on the board, it seems like a total waste of time.
Because we have everyone doing it together, so we have you give us the right answer.
That's mostly true, yeah. And the fact is, the person holding the chalk is
Teacher.
me, right? So if you say something weird, I'm probably not
Gonna write it down.
gonna write it down, okay? On your homework papers, there probably are some weird things that you write down from time to time, or on a quiz, or on a test. Sometimes you write things that are a little bit off the wall. But in class, you sometimes get the feeling, I don't need to check it, these are just all right all the time. Well, it's partly because the wisdom of the group and the person holding the chalk is contributing to that. So this one, what are we looking to write? What's our
7.
opposite?
7 minus 10. Or 10 minus 7.
We're gonna add or we're gonna subtract?
Subtract.
We're gonna subtract, so show a little subtracting on both sides. The magic number to be subtracting with
7.
is 7. Since the problem added 7, you're gonna subtract 7. A little bit of zeroing out. X, we hope, equals 3. Check it. 3 plus 7, is it indeed 10?
Yes.
Yes. Question about that? This one sometimes makes people mad. Why does this one sometimes make people mad?
Because it's the wrong way.
Because it's like the wrong way, or backwards, or however you want to look at it. So we had a property early in the year that told you could just switch them. And there goes the chalk. What was the property that told you could just switch them?
Is it the false?
Community?
No, we're switching the two sides of
Associative.
equal.
No.
If A equals B, then B equals A.
Oh, symmetric.
There's a symmetric property. So if this being backward or out of order or the wrong way or whatever people said makes you mad, just don't write it as 3 equals. Write it to have an equal 3. If that doesn't bother you, then just leave it as 3 equals. It doesn't really matter. What does matter is your attention should always go to the variable. The variable is running the show. So if the variable is subtracting, the job in your world
It's add.
is adding. And since the variable had 4 with it, you have to deal with the 4. The 4 just has to happen to bump into the 3 because whatever we do to one side,
Do to the other.
we have to do to the other. So 3 and 4 have to interact eventually. But 3 is like a supporting actor. It's a minor character, guest star on this show. The 4 is running the show. The 4 is what we're after. So the variable was subtracting 4. We're going to add 4 to do the opposite of that. Zero that out. X stands alone.
7.
We got a 7. And then try it. 7 minus 4 is indeed 3. So check these. Something there. How are we going to attack the next one? Subtract 10. Subtract 10 under the
5 and
the 5 as well as under the 10. We're going to cross out 10 and 10. This side is just left with X. And this is the first one that gets beyond the like baby add and subtract rules. 5 minus 10 causes a little bit of problem sometimes. It is negative 5. If you do your add rule to check it, adding a negative and a positive, what was that rule?
Depends on big.
Depends on bigger and we subtract. So negative 5 and positive 10 adding, is that indeed 5?
Yes.
Yes. So that checks out and we're done with the column. 1 column down, so we're 2 to go. Something there. So this one, what are we doing on this one?
Adding 5
Adding 5 under
with negative 2 and a 5.
negative 2 and the
5.
5.
You cross out the 5.
Ditch out those 5s.
And x equals 3.
X would equal 3. If it's an adding that we're doing, think about the adding rules. It's a negative adding a positive. Depends on the bigger. We subtract. We're coming out with 3. But when you check, you're thinking subtract rules, because it was a subtract problem. 3 minus 5, is that indeed negative 2?
Yeah.
Yep. Something there. Next one.
We subtract 4 and 2/3.
Subtract 4 and 2/3 both ways. Get rid of those. X equals.
5 and 1/3.
What'd you say?
5 and 1/3.
It is. If people have trouble navigating to 5 and 1/3, anybody remember like 7th grade style how we did that subtract? Because it's a little bit, sometimes people think 10 minus 4 should be 6, and maybe you should be dropping the 2/3 because it didn't have a friend. Any memories or justification how it's 5 and 1/3, which it is?
Make it 9, and then the fraction would be 3.
Correct. A little bit of borrowing. Just like if you were taking 100 and subtracting 42. You know, you can't do nothing minus 2, so you borrow and help. Okay, borrow from 10 makes 9, just like here it made 9. And then in fraction life, 3/3 is a fair trade. We borrowed one, we put in 3/3 to replace the one that we borrowed, and that's an even trade, and then math can help that go. Checking it, the 5 part and the 4 part makes us up to 9. The 1/3 and 2/3 added makes
But
1/3 and 2/3 will make 3/3, in other words, a full 1. And the 5 and the 4 was 9, 9 and 1 makes the 10, and that does check. Something there. This is a brief exception. I would not start off this one immediately just jumping on my opposites. What might you be better to tune up on this one before you even think opposite?
Minus minus makes plus.
Minus minus makes plus. Just clean that up. That minus minus is sort of an eyesore. Just jump immediately on that, make it a plus, and then it's subtracting went out the window. But, except, since the problem is adding, now you have to subtract. So we're going to subtract 10 both ways. Eliminate. X would equal 30 is true. 30 plus 10 is indeed 40, so that does check. This one is a little weird. There'd be 2 ways that you could think about this one in terms of what we're doing. Suggestion? It's where we're headed. We're on a road to 14.2, but how can we justify that?
Loss of 2/3.
You're subtracting or adding?
You subtract within the minus.
Yeah. Okay, so one way you could think of this is, I see the variable adding, so your initial instinct is you have to subtract. But the number you're subtracting is a negative. So you could either write down that you're subtracting negative 2.3, or you could kind of recognize minus minus makes you plus. To get rid of a negative 2.3, adding 2.3 would do the trick. But whether you choose to write that with a minus minus thing, or whether you choose to just jump straight to the plus thing, either way, that's going to wipe out. But you are subtracting a negative, but that is forcing you to add. So how you show that, I'll leave that up to you. X does equal 14.2. That would check out. If you had a negative adding a positive, how would that work? How's negative adding positive work? Subtract. So if you couldn't do it in your mind, 14.2 subtracts 2.3, how would you math that?
You take 1 from the 14, bring it over to
14 becomes 13, make the 12, do the borrow, it is 11.9. Question about that. One more column. First thought on this,
Minus minus.
I'd go minus minus makes plus, and just fix that right away. So since that's now an adding on the board, in your algebra life, it's now
subtraction.
subtract. So we subtract 7.1, gone, X is left,
2.1.
2.1. If we check it, 7.1 and 2.1 would make 9.2, that does check. Question about that? This, we're going to have a difference of opinions. There's going to be maybe a way that your instincts take you, but it might take you a little longer. Or there's going to be like a shortcut way to go, but maybe people will be uncomfortable with it. So I'll give you two options of how you could solve this problem, and then you pick what you like. Anybody have a suggestion on something that you could do to try to take this thing on?
You see the first one, and then you see that the 3 becomes a 13, so you just add 10 onto the 7.
Okay, so if your algebra instincts are sound, then yes, that's going to be the quickest way for you to solve that. If people didn't hear or understand what she said, does anybody have another way you could go on this?
You can subtract the x plus 3 minus the x plus 13.
Okay, so if you want to do more of what we've been doing all period, what you could do is think about doing opposites. If they're going to add 3, you can subtract 3. So if you subtract the 3's, you come out with x being 4. If x is 4, you could figure this out by take the 4 and
Add it to 13.
yeah, just stick it in. 4 plus 13 is 17. If you're comfortable with that, because it's more like we've been doing all period, that's fine. You could fully solve for x, and once you get to x, stick it into the other part of the problem and see where that takes you. Nothing wrong with that. That's completely fine. It's more like what we've been doing all period. It's less maybe creative or instinctive. Question about that? Okay. What she did a second ago was think more like back to the scale stuff and trying to recognize what happened to change the one side, and then let me just play along. So this had x plus 3. Then later it has x plus 13. So what did somebody change about this side? It went up by 10. So if the one side goes up by 10,
The other side also has to go up.
the other side has to go up by 10. And that still gets us to the 17. All roads lead to 17 on that. I would do the, hey, it went up by 10 move. But you don't have to do it that way. Something about that. So one choice on this would be, go ahead and figure out what x is. X would be
X would be 11.
11. And if x is 11, then 11 minus 5 is 6. That's not what I would do personally, but if that's where you're more comfortable, then do that. Get the x out of the one problem, and then stick that into the other part of the problem. Something there. This is what I would do. This had x minus 1. This now has x minus 5, which means this went up or down? Down. We were subtracting 1, now we're subtracting 5. We've gone down. How much more have we gone down into the hole over here? We've gone down 4 more. So if this went down 4, the other side has to go down 4. We'd still land at 6. If that confuses you, don't do that. But if you like that, then do it. Something there. Last one of the day. There will be a problem or two at the end where they'll tell you a story and you'll make your own problem up. We've been doing this last chapter already. We just didn't have to solve them. Today we did. So sum means add a number, x, 10 is
Equals to.
equals, and then we got a 14. If it's a make your own problem, I don't care if you show the work to solve it. If you just get the number, I'm happy. The magic number here would be 4, because we're going to subtract the 10. That's what we're doing. Today's all adding and subtracting. Do the opposite, do the same to both sides, show the work, because we're really trying to get these ideas jammed into your brain hard of doing opposites and doing the same to both sides and check. Tomorrow, almost the same thing. We'll just multiply or divide. Homework where we go today, and there's still a ton of time left, about 20 minutes if you want to jump there. We're on page 98. We're going to do evens for most of the beginning part. So from 2 to 36, we're going to do evens only. 43 to 46, I'm going to do all 4 of them. 43 to 46 are like these 2 that we did almost at the end, where we had 2 ways to do it, and you pick what you like best. And then we're going to skip a little bit more. and then finish from 53 to 56. 53 to 56 are like this last one I did, that they're giving you a sentence, so you have to create an equation and then solve it. So the 2 to 36 even, I definitely want to show the work, the cross outs, the x equals, check marks, the whole bit like we did on the board. 43 to 46, I'm giving you freedom. I don't know what you want to show. Different people are going to go different ways, so I don't care about the work on that. But the last four, I definitely want to see not just a number, but the equation that led to the number. So those last four, write an equation, and then have a number to boot.
What page was it on?
It's on 98.
And it was
2 to 36, just evens. Then we skip a few. 43 to 46, do all four. Skip a few more. 53 to 56, do all four.